All right, so remember in our last lesson, we looked at an experiment where time was measured, the amount of time it took a person to move a cursor from some starting position to some other marked position. So what length of time did it take the subject to make that move? And remember, the subject did it 20 times. There were 20 trials in the experiment. So 20 times, maybe I shouldn't use an X, that looks like a polynomial. 20 times the experiment was run. And we got a histogram because since no one is going to hit in milliseconds the exact same time every single time they try, if we use discrete methods for describing the situation, we would just end up with 20 points that represent one time for each speed. So instead, we wanted to use a range. And so I'm not going to label this histogram because I just want to talk about this in theory. I don't want to talk about the specific experiment, just making a point here. So say you run the trials and you find that 10 times the experimenter, the person who ran the subject, 10 times their speed fell within whatever this range is. And this would be, say, 8 times it fell within this range of times, and so on all the way to the end until you've plotted all 20 times. This is a perfectly reasonable way to represent 20 trials in an experiment of this type. And these values, the histogram, the height of the histogram was actually at each range was actually determined by the experiment. You didn't know ahead of time how long or how fast the person would be able to move, or even the range of times, depending on whether they just first started or they were in the middle or they were at the end, maybe they got bored, whatever. You had no idea what was going to happen. This histogram describes the situation after the fact. And we use the histogram when the variable is continuous. So this histogram is an amazing way, perfectly excellent way of describing the situation as it occurred. But what if you want to look at the probability or likelihood that a particular event in the future, right? So that a particular event will occur. So running an experiment like this is only valuable if we can make predictions about something else, the same situation in the future somehow. What we really need is a way to represent all the potential times it could take to move a cursor from a starting to a finishing point. So we're looking for all potential times. Or all I can say this, all potential outcomes if you were to run the experiment again or observe someone in the real world making this motion. So data like this that come from a continuous variable will produce continuous distributions. And one very important type of continuous distribution is called the normal distribution. That's a U. A normal distribution has another name commonly used called the bell curve. It doesn't have anything to do with an actual bell, except that it sort of has the appearance of a bell once you look at it. So right now, we're not going to create a normal bell curve or normal distribution curve, but we are going to talk about how to read them, what they mean once you see one. So let's start with the most basic, perfect, average bell curve. It'll have a high point someplace in the middle, and then it'll slope off to both ends, and it'll duplicate on the other side exactly the same thing. So you can tell this looks like a bell that's been placed down. You can imagine if I had a handle here, I could pick it up and ring it. That's why it's called a bell curve. It has nothing to do with bells, but it does look like a bell when it's in its most perfect form, which is this form. And notice here at the bottom, well, let me be a little bit clearer in my representation. So this would be like an x-axis, right? It goes on forever and ever. And the bell curve doesn't necessarily touch. In fact, the bell curve doesn't touch. It just gets closer and closer as though the horizontal line you're looking at is an asymptote. And across the bottom, just like on the histogram, you would have values that would represent a range of values. So say I've got 20, 40, 60, 80, and 100 here, and however long it goes. So these parts don't touch, they just get closer and closer, and they never actually become zero, because presumably the probability of getting zero isn't zero, right? You would think that zero would be a likely chance, but we're assuming that the experiment actually runs, that the person didn't start with their cursor here and then go, nah, I'm going to go to lunch. They actually ran the experiment. But still, you allow for that down at the end, the probability. So it just gets smaller and smaller and closer to zero, but it doesn't actually ever become an absolute zero. At a speed of something like way down here, 0.000007 milliseconds is highly unlikely. It's possible, but it is highly improbable. And so that would fall, these values would fall down here where the normal curve is really, really close to the x-axis, representing that there's not a lot of probability there, which may not make sense yet, but the next thing I say I think is going to make you go, wow, that's amazing. So underneath the bell curve, and let's imagine that it actually touches so that I can say this is a closed area, underneath the bell curve represents every possible outcome that could occur, every possible time that could occur, including way over here, it could take 1,000,000 seconds. 1, 2, 3, 4, 5, 6, 1,000,000 seconds, so milliseconds, then that would be, I think, 3 more. So it could take forever to happen. Not very likely, so it falls way down here in this skinny part, but still, it's a possibility. If I were able to take the area under the curve, it represents every possible possibility of occurrence for an event. So since everything is encompassed in the area under this curve, we can say that the area under this curve equals 1. Now that may not seem automatically natural for you to think about, but really we're saying 100% of the possible outcomes exist somewhere under this curve, or this curve represents, it doesn't exist there, but they represent every single possible outcome. Well, 100% of outcomes, if I divide that by 100%, because we don't want to deal in percents, but we want to deal in the decimals of percents, then that equals 1. So we're going to work with decimals as a percent. So the area would be considered, under the curve, would be considered 1 as a representation of all the possible outcomes. And you can imagine that the vertex or the apex of this bell would represent the exact or the perfect time, the time that happens all the time, the most represented time, the normal amount of time it would take to go from here to here with a cursor, with a mouse cursor. And so this is the optimum, the most often occurring time, and it falls somewhere, we don't really know where. But suppose you want to know maybe what is the probability of this random time here occurring? Well, on the bell curve, if all of the curve represents 1 or 100%, then I can choose some range around that point, or that actual time I'm looking at. I can choose some range, and if I find the area of this column, it will tell me the probability as a percentage of 1. It'll tell me, or as a percentage, it will tell me the probability of this point, that outcome occurring. Using the normal distribution curve to examine the probability of some random thing happening, some random number occurring. Now, let me blow your mind. Suppose I want to know what's the probability of this exact value occurring. That exact value, not the probability in the range of possibilities, but the exact value. Well, that exact value would be a rectangle, or, it would be a rectangle with a sloped top, so rectangle-like shape. But that exact value would only have a height. There would be no width, because we're not talking about a range. And so the probability, the good news is in probability, we'll learn notation soon where we don't have to write probability out as a long word all the time. The probability of this exact value occurring equals the height times the width is 0 equals 0. So there is 0 probability of an exact value occurring when you use a normal distribution to evaluate and predict from an experiment, data obtained from an experiment. How cool is that? All right, let's move on. So I've sketched here a perfectly symmetrical normal distribution, meaning that from the top, as perfectly as a human can sketch, from whatever the top peak is, it's exactly the same thing on the left as on the right, as the slope, as the bell curves down. So this would be a normal symmetrical distribution of data obtained from an experiment. Where if I use this original example or original experiment as an example, I could say, oh, most of the time, the highest probability, most of the time, the time it takes to go from point A to point B in this experiment is whatever this apex value is. So most of the time, that's what's going to happen, because that's going to have the highest area right around that top point. And then sometimes the person doing the experiment is going to just be pokey. Instead of doing maybe 10 milliseconds, completing the task in 10 milliseconds, suddenly this person is going to complete the task in 7 milliseconds, or 5, or 4, or 3, or just fall asleep in the middle of the job and take a day. So the left-hand side represents any slower occurrences, and notice that they are a smaller value, right? So to achieve this little tiny rare event is going to have a smaller area for the column, and it's going to have a lower probability of occurrence in the future. Then same thing on the other side. Sometimes the person's going to regather themselves and commit to do it as fast as they can, and they're just going to zoom, zoom, zoom. And again, they're just going to zoom, zoom, zoom. And the other side of the curve represents the possibility of those perfect occurrences that are super fast. And maybe 100 milliseconds would be, there's a possibility of it happening, but the probability is really low because this area is really low. So this is a a very symmetrical normal distribution. They rarely come like this. They can be forced into this kind of a pattern, and we'll do that. We'll look at that when we work with normal curves later. Most of the time, the data has a skew to it. And you can imagine, if you go back to our original data, if I were trying to make a bell curve here, it would have to look something more like this to represent the data. And you can see that this little curve here, where the left-hand side is very steep. So this says that most of the occurrences are actually going to happen here toward the left, the values represented here toward the left, and then fewer and fewer and fewer possibilities will happen off to the right. So this is called a skew. In this case, I'm going to sketch it a little bit so we can look at it more clearly. So this would be like a skew where most of the values are on one side or the other. Let me do it again. Like that. And so you can see that the center of the data doesn't fall at the apex of the data. And so this data is skewed. And this skew in particular, well, let's look at it over here. This skew, the sloped part, the part that's not very steep, but that slopes off slowly, this is the skew region. Or the region of skew. So since the region where the skew occurs, where data stretches out, since that region is the skew, we would call this skew, on this example, a right-hand skew. Or to the right. So this would be a skew to the right. Or another way to express it, some books and some people prefer, rather than to the right, prefer the fact that when you go to the right on a graph, you're always going to the positive. And so this would be a positive skew. I've had multiple teachers and multiple books in this arena, and so I use both words interchangeably. I don't really care which word you decide, which way you decide to describe it, as long as you describe it more clearly than I just described what I tried to say. But if you just remember that the tail, the long tail, defines whether it's a right or a left skew. So you can easily imagine that a skew that looks like this would be a left-hand skew, or a negative skew, because the skewed region is on the left-hand side, or toward the smaller numbers. So one last variation on a normal curve. It's kind of a fun one. If I look at, I'm going to sketch in the histogram for it. So we have this data. There you go. And I'm just going to show you the two peak ranges. So this is 1.75, and this other tall one is 4.25. This is called bimodal. Distribution. And it's kind of a fun one. It's the frequencies of times between eruptions of the Old Faithful geyser. So it has two types of peaks. It has a lot of really small geyser blasts. I don't really know the right phrase for that. So you'd have a really high peak with a skew to the right, or a positive skew, followed by a pretty symmetrical second peak, maybe a little bit of a negative skew, but a pretty symmetrical second peak. And so you would get a double peaked normal distribution for that. And one last thing, a definition. I don't know that you'll ever need it, but I just think it's kind of funny, so I'm going to give it to you anyway. So when a shape when we look at the tails of a normal curve, you might have, let's put it up here. So you might have a curve that has a very low endpoint, or both endpoints are very low, and then suddenly you get really high points, and then suddenly low points again. So this would be a super extended bell curve. It's very skinny and very high. It stretches out kind of symmetrically on both sides in this example, but this is called a leptokurtic. How's that sound? Leptokurtic. It's like watching The Big Bang Theory. And then another distribution has maybe a tiny little amount here, jumps up, has a number of higher values, then drops back down and has a low value. And so in this case, you get one that's wider compared to its height. So you get a lot of width. And that width, that shape for a normal distribution is called platykurtic. Okay, there you go. Anything you ever wanted to know about normal distributions?